I hope you enjoyed our introduction to the world of continuum properties. We now shift one gear up and progress to the next important concept, the analysis of the speed of the particles. As you can see here on the left, individual particles, shown in black, in one region of interest, here shaded in gray, may have different velocities. Hence, we can define an average particle velocity by weighting individual particle velocities with the volume of the individual particles, as illustrated in red on the left. This is equivalent to a momentum-based averaging, since we assume identical particle density and hence volume and mass-based weighting is identical. Most important, also the fluctuations around this average speed matter, and that is why we need to define a particle velocity fluctuation tensor, shown here in green. This tensor is calculated as the dyadic product of the average velocity fluctuations u prime in an RVE, which is here the gray region. Most important, these fluctuations quantify the particle-to-particle variability of the particle speed. It is, and this is very important, not a temporal fluctuation of the particle velocity. In a similar manner as for the pressure, one can then define a scalar metric that quantifies the magnitude of these fluctuations. This scalar metric is the famous granular temperature T. T is essential in many theoretical models, and the key message is that when using the DM, we can generate data, for example that of the particle velocities, that can be used later to calculate T and hence help theory evolve. Next, an important difference relevant for DEM-based data analysis is illustrated in this graph in the center. Here we show the time evolution of the average particle speed in red and that of the velocity fluctuation tensor in green. As you can see, we can also average over time, making transparent different dimensions of averaging, in space or in time. Clearly, we must not confuse a local average quantity with a time average quantity, since these quantities can have very different meanings. To sum up this slide, defining particle velocities relevant for continuum theory should be done in a careful way. We next dedicate our attention to the stress in a granular material. The first question that arises is, how can we measure the stress? In fact, multiple options exist to do this. First, we can calculate the stress from discrete particle simulations, such as the DM. This is computationally expensive, however, as you know, the DM is now in widespread use. The large interest in this option started around the year 2000 and is still ongoing. The second option is to use theory without any additional data, most often starting at a fundamental equation such as the Boltzmann equation. This option works only for relatively dilute flows, for which certain assumptions hold and analytical calculations can be done. Despite the fact that there are still theoretical developments, research on equations for the particle phase stress has leveled off significantly in the last 2 decades. Third, and this option is quite obvious, one can attempt to determine the stress based on real-world experimental data. This brings us to the famous experiment of Bagnold in 1954, in which particles were initially mixed with a liquid to suspend them and to prevent them from sedimentation. Subsequently, he sheared the suspension in a cylindrical device. While his experiment was far from perfect, he could already measure normal and shear stresses in this granular viscosimeter at different shear rates. Nowadays, a plurality of testers exist that aim at measuring the flowability of a granular material in some way. Unfortunately, the stress response of a granular material is so complex, and hence a perfect granular rheometer does not exist even as of today. This fact again stresses the message behind this slide. Calculations of the stress based on discrete data, and exactly this is what the DEM can deliver, are the most important source of information for the development of granular stress models. So let us dive into how this can be done. You will see it is surprisingly easy. The particle phase contact stress is defined as a double sum. First, we sum over all contacts of a particle. Specifically, we sum the dyadic product of the contact force and the vector L superscript PC. The latter is a distance vector pointing from the center of the particle to the contact location. Both pieces of information are readily available in a DEM simulator. This sum is then multiplied with the weight W sub p delta V, which quantifies how much each particle contributes to a certain RVE delta V. We then sum over these weighted particle contributions and finally divide by the volume of the RVE, denoted here as delta V. On the lower right, you see an illustration of a particle with 4 contacts. The distance vector LPC and the contact force vector F superscript C are displayed only at the first contact. The weight is here illustrated only conceptually. It takes into account the distance between the center of the particle and the cell center. In this case, the weight will be close to unity since this difference is small and the particle is almost completely in the CFD cell. Let me close with 2 notes. First, we have introduced a minus in above equation such that the compressive stress is positive and a rarely observed stretching stress would be negative. Second, what I have shown here is only the contact stress. Particle velocity fluctuations cause an additional kinetic stress. This kinetic stress, however, is only relevant in comparably dilute flows with few or no contacts. We will hence not discuss it in detail, and let us now progress to the next important quantity. When talking about the stress, we speak of a 3x3 tensor, i.e. a rather complex description of the stress state. In order to make the stress easier to interpret, one often defines a simpler scalar quantity. This scalar quantity is the contact pressure, which is defined via the trace of the stress tensor, i.e. the sum of the diagonal elements. In other words, the pressure is the average normal stress in an RVE. As you can see in the figure on the right, the pressure is correlated with the normal forces. Also, it is clear that the pressure increases with increasing distance from the free surface. This is similar to what happens in a liquid, specifically what we would call the hydrostatic pressure in a liquid. We will see that there are quantitative differences between the hydrostatic pressure in a liquid and a granular material. However, the concept is similar. Also, for liquids, the pressure is often sufficient to quantify the stress state. In contrast, and as we will see later, for granular materials, the individual normal stresses differ significantly, meaning that the pressure can describe the stress state only to some degree. Finally, it is important to not confuse the pressure with the normal stresses. Again, the pressure is just an average normal stress, and in granular materials there can be significant normal stress differences even in the static configuration. But let us now progress to flowing granular materials. To showcase the complex stress response of such a granular material, I would like to introduce the regimes of stresses in granular shear flows on this slide. The regime map I will show you is based on DEM simulations in a simulation box with constant volume to which a simple shear flow is applied. This means shear happens only in one direction and so-called Lees-Edwards boundary conditions are applied. The latter are specific boundary conditions that I will introduce in a minute. The pressure response from such shear simulations is shown here on the left. Note that the different symbols and colors refer to different particle volume fractions phi p and hence indicate different concentrations of particles in the box. Also note that both the shear rate and the pressure is made dimensionless with adequate reference quantities. For the pressure, this is the stiffness parameter of the contact force model Kn divided by the particle diameter dp. The shear rate is normalized in a more complex manner involving also the stiffness. As you can see, the logarithm of the pressure is linear in the logarithm of the shear rate only in relatively dilute flows, indicating that the kinetic stress we have mentioned before briefly dominates in this regime. Also, the pressure increases with particle volume fraction, which is quite intuitive. However, above a certain particle volume fraction, the stress regime changes as illustrated by the black curve. In this dense regime, the pressure and also other components of the stress tensor do not depend on the shear rate. This regime is hence called the quasi-static regime, and as you can imagine, the kinetic stress is completely irrelevant in this regime. The third regime is the one at high dimensional shear rates, where all the curves converge. It is called the intermediate regime. To round up this excursion to the stress regimes, I would like to close with three thoughts. First, as you will see from a quantitative analysis of the dimensionless shear rates in practical applications, in most practical cases involving solid particles, the dimensionless shear rate gamma star is very small. i.e., we are either in the dilute or in the dense regime. The intermediate regime is never accessed by such flows. Second, only in case of very soft particles, e.g. gels, soft protein particles or emulsions, the intermediate regime can be observed and the material behaves differently. As you can see, the slope of the pressure with respect to the shear rate is lower. Third, you might wonder how the other components of the stress tensor behave, for example the shear stress. Indeed, qualitatively similar regime maps can be drawn for the shear stress. Thus, there is nothing fundamentally new for the other stress components.